Assalamu alaikum. Welcome to lecture number 14 of digital signal processing. In the previous lecture, we have discussed regarding the analysis of signal and its basic terminologies. And we have also discussed some techniques utilized for signal analysis. And then we have started our discussion on Euler's identity, as we have concluded that we are going to perform signal analysis by using Fourier tool. So we have discussed basic Euler's identity, and using that identity we have actually converted our signal into frequency domain. So resuming that discussion in this lecture, and in this lecture we also cover continuous time Fourier series. So students, by using Euler's identity, you have observed that we have actually converted our frequency to a time domain signal into frequency domain. Another interesting thing is that we may decompose any exponential signal, or we can say any complex exponential signal, because it is written here e raised to power minus j 2 pi f naught t into sine and cosine wave. It means that sine wave and cosine waves are added up together to formulate a complex exponential signal. And at the end of this slide, you came to know that sine wave or cosine wave have double-sided spectrum, but for the complex exponential signal, we have only a single-sided spectrum, and its magnitude is same as that of the original signal. So recall that we have concluded our discussion that we have these phasors for the sine waves and these phasors for, or these spectral lines for the cosine waves. Now using this identity, cos wave is added up to sine wave to get a complex exponential signal. But before adding, sine wave is multiplied with a factor of j. So it simply means it is multiplying with positive j. Positive j means the spectral lines are going to shift their orientation by 90-degree counterclockwise, because it is positive j. So it is just a plus 90-degree phase shift or counterclockwise phase shift, because counterclockwise is assumed to be positive. So you can see that this is the actual frequency domain representation of sine wave, and after multiplying it with j, these two phasors are actually shifted counterclockwise by 90-degree. This phasor, which is parallel to the y-axis or imaginary axis, is now converted into a phasor which is parallel to the real axis, as it is the 90-degree phase shift. And similar is the case with this second spectral line. It is multiplied with j, means it is shifted 90-degree counterclockwise. So this is basically the frequency domain representation of positive j sine 2 pi f naught t. Now we have to add up these two representations, because first one is for cos and second one is for j sine 2 pi f naught t. and we are actually adding up these two waveforms to get the complex exponential signal in the frequency domain. So you can see that this spectral line is at minus f naught, this spectral line is at minus f naught. So both of these spectral lines are at minus f naught and both are having the same magnitude, which is half. So these two basically lines, spectral lines, cancel each other effect, and the net result is zero spectral line on the negative frequencies. But if you look at the positive side, we have the spectral line at f naught for sine plot as well as cosine plot. So these two spectral lines actually added up, and these spectral lines is having the magnitude of 0.5 previously, and when they are added together, then the strength or amplitude becomes 1. So you can see that we finally have the spectral line present only on the positive f naught and the magnitude is 1. So you have observed how interestingly the Euler's identity actually convert cosine signal into frequency domain, and again these two frequency domain representations are added up to get a complex exponential signal or frequency domain representation of complex exponential signal. Continuous time Fourier series actually states that any periodic continuous time signal can be split up into sinusoidal components which may be infinite if the signal is really complicated, but it guarantees us that any signal can be represented in terms of sine wave and cosine wave. As you can see from the plot, we have a square wave signal which is not perfectly the square in shape, shown from the black color and highlighted by my pointer. You can actually assume this as a square signal or square wave. However, this is not a perfect square wave, which the Fourier is also claiming that for a perfect shape you may need infinite sum of sinusoidal components. But here we are adding up few components, that's why we are getting the approximate shape of square wave. If we are going to add up more sinusoidal components of different frequencies and amplitudes, then we will get the perfect or nearly perfect shape of a square wave. But as we are very limited in our resources and that we do not have this much memory to store infinite sum of sinusoids or infinite sinusoids, and we cannot process that infinite sinusoids, so we are actually going to see the sinusoids which are actually affecting the shape of the signal, or we are just assuming that sinusoids which are basically contributing most for this shape of signal. So the remaining one can be discarded as far as analysis is concerned, but again it depends upon the application that how much number of sinusoids we are going to retain. So it completely depends upon our application. So but you have the idea now that any signal can be represented by means of adding individual sinusoidal components. You can see from this plot also the x-axis is basically showing the time domain, whereas the y-axis is basically the amplitude, which is basically, you can see here, it is the amplitude, and z-axis is basically the frequency domain. So it is basically a 3D plot in which you can observe that if we talk about the time axis, then first waveform, which is having the frequency of 5 kilohertz, it added up to another waveform having some higher frequency mentioned as 15 kilohertz. Then these two waves are added up to the third wave, which is of 25 kilohertz, and so on. You can see that as you move from this to this side, the frequency is increasing but the amplitude is decreasing, which actually all the wave combine together to form this waveform. So if you want to look at the 2D look of this waveform, you can have this at this side. Basically this is the complicated waveform, which is a square in shape, and we are adding up multiple sinusoid to actually get the square wave in the output. So this is also the claim of Fourier, that any signal can be decomposed into infinite sum of sine and cosine waveform. And along the z-axis you can observe that this signal is basically classified according to its frequency parameter. Means if this is basically the frequency axis, frequency is increasing this way, this is 0 frequency, 1 4 1 2 3 4 5, and this is exactly the 5 hertz 5 kilohertz, and you are getting a spectral line at 5 kilohertz, and its strength is more as compared to all these spectral lines, because this wave is contributing the most towards this shape of square waveform. So this spectral component, which is of 5 kilohertz, is present in this signal, which is affecting the most as far as the complicated waveform shape is concerned and frequency is concerned. This first basically component is contributing the most, as it has the major strength as compared to all those. However, all other components are also contributing to form the complicated wave, but their contribution is less, and each component has its own contribution, and each component is having different frequency and different contribution to form a square waveform. So we have basically two set of information in this 3D plot. One is for time domain and the second one is for frequency domain. Time domain waveforms are actually combined to form the square waveform, and Fourier states that this square waveform can be split up into infinite sinusoids of any frequency or amplitude. So we are actually, by using the Fourier tool, we are actually getting the information of frequency content present in that signal. We are actually getting this spectral line information with the help of Fourier series, that this frequency component is present in this signal. By looking at the shape of the signal, we can never tell, or we can never claim that 5 kilohertz frequency is present in this signal. But by looking at this spectral lines, we can claim that 5 kilohertz component is present in this signal, and it is also contributing the most. However, 15 kilohertz is also present, 25 kilohertz is also present, and many other components are also present in this signal. So by this information, we are actually talking in terms of frequency components or frequency magnitude, which is the essence of Fourier series. And we can analyze many things with the help of this frequency. Now we are going to derive the expressions for analysis equation and synthesis equation of continuous time Fourier series by considering a generic example. So with the help of this example, by considering general case, we actually come up with the result which is exactly the same as of Fourier series. And by this we will understand this concept more clearly. So first consider the case 1. We have 4 sine waves and the frequencies of these sine waves are assumed to be 2 Hz, 4 Hz, 6 Hz and 8 Hz. We have taken this value arbitrarily, so any other values can be taken, but for understanding purpose we have taken these values 4, 2, 6 and 8 Hz. And all these waveforms are actually added up to form a complicated waveform. So if we are going to express one waveform or one signal which is of 2 Hz mathematically, then this expression can be used, which is written on the slide. x1 of t is basically denoting the first signal, and it is basically comprises of the amplitude v1 and sine omega 1t. Omega is basically representing the angular frequency. You may transform it into 2 pi f1t, and this signal is basically this expression is basically the mathematical model of the sine wave having 2 Hz frequency. Similarly, we can represent the sine wave of 4 Hz frequency with another mathematical model such as x2. The third wave of 6 Hz can be represented with another equation, and we have denote it as x3 here you can see, and the fourth waveform of here 8 Hz is represented as x4. And if we want to write the complete expression for all of these models or sine waves, so we can write b1 sine omega 1t instead of x1t, because x1t is our first sine wave of 2 Hz. So we have write b1 sine omega 1t instead of x1 of t, and instead of x2 of t we have written b2 sine omega 2t, b3 sine omega t3 and b4 sine omega 4t for all these 4 waveforms of 2, 4, 6 and 8 Hz. But you can also see that if omega is considered to be 2, then for the second wave omega is 4, then we can represent actually 4 in terms of 2. That is, omega 2 is basically omega 2 is 4. Omega 2 is basically 2 of omega 1, or simply 2 of omega, which you can see here. Similarly, the third frequency, which is omega 3, can be represented in terms of omega 1, which is 2 Hz. So omega 3, which is 6, is equal to 3 of omega 1, which is written here. So generally we have considered omega as the fundamental angular frequency and represent all other frequency in terms of that frequency. So in this way we have a single frequency content or single frequency notation used in this. However, we do not have only single frequency present in the original signal. We have 2 Hz, 4 Hz, 6 Hz and 8 Hz, means 4 different frequencies are present, but all these frequencies are represented in terms of a integer multiple of single frequency, which is actually the essence of Fourier series. Fourier series states that any periodic complicated waveform, it can be represented into sine and cosine waves, infinite sum of sine and cosine wave. So we are actually representing the fundamental frequency and all other frequency in relation to that fundamental frequency. So in this way, this signal can be represented by this equation. The final signal, if that is the complicated waveform, after adding up these two waveforms, is x of t. Or we can say we have other frequencies as well in the signal, and we add them all to get a complicated waveform. So this type of signal can be represented by a general mathematical equation written as this. We have n number of sinusoids present in this complicated waveform, and we are actually adding up all these sine waves component to get our final output. Here you can see that all these have different amplitudes denoted as B1, B2, B3 and so on till B1. But frequency is represented in terms of fundamental frequency or fundamental period and integer multiple of this frequency, which is 2 omega, 3 omega, 4 omega. However, it is not necessary that all these integers must be present, that 2 omega must be present in that signal. Maybe signal is not that shape that it may contain 2 omega, it may contain 3 omega, 5 omega, 7 omega, it may only contain odd harmonics, it may only contain even harmonics, or it may contain even plus odd harmonics. So it depends upon the nature or shape or pattern of the signal, that which frequency contents are present in that signal. So generally we can represent this equation as all the components added up to yield the final output, which is x of t. Another important thing is the fundamental frequency, and fundamental frequency is related to the frequency of the fundamental wave or first harmonic. And what is the fundamental wave or first harmonic? The biggest waveform which is of maximum time period and minimum frequency. It means here 2 Hz is the fundamental wave or first harmonic, because it has the lowest frequency, or contrary we can say it has the longest time period to complete its one cycle. You can imagine that if we have 4 waves, 2 Hz waveform, 4 Hz, 6 Hz and 8 Hz, then the longest time to complete the one complete cycle will be taken by waveform of 2 Hz. So the longest time period waveform is basically the fundamental wave, or we can say the first harmonic. Another interesting thing is, if the complicated waveform is purely odd symmetrical, it means it has odd symmetry, then its constituent elements or ingredient element must have the odd symmetry in them. It means if we get the waveform after adding up these 4 waveforms, and that complicated waveform is of odd symmetry, then it is of no doubt that these 4 ingredient elements must have odd symmetry. That's why we are getting odd symmetry in the final waveform, which we get after adding up all these constituent or ingredient elements. Now coming up to the second case, which is case 2. In case 1 we have considered 4 waveforms which are having frequency 2, 4, 6 and 8 Hz, but they are sine waves. But for case 2 we are assuming 4 waveforms, the same frequencies, but these are cosine waves. It means previously all the waveforms are starting from its minimum value, because sine is always started from 0 if there is a 0 phase shift. That is, if theta is equal to 0, in generic expression we have represented sine wave as x of t is equal to a sine omega t plus theta. So theta is phase shift. So is if phase shift is 0, then sine is basically starting from the 0 value, and gradually it increase its value towards the maximum. But if we consider the cosine waveform, then it actually start up at its extreme value, which is 1. So here we are adding up the 4 different frequencies cosine waves to get a complicated waveform. So amplitude is different. Amplitude is represented by A1, A2, A3 and A4 respectively, and again frequency is 2, 4, 6 and 8 Hz, which can be represented by omega 1, omega 2, omega 3 and omega 4 respectively. And we can also represent all these frequencies in terms of the fundamental frequency, and fundamental frequency is that frequency which is of the waveform having the longest time period or the minimum frequency. And here again minimum frequency is 2 Hz. So it means the 2 Hz waveform is our fundamental wave or first harmonic. So it can be represented as x1 of t is equal to a1 cos omega 1 t, or simply omega. So similarly, as we have discussed for the sine waves, all these 4 waveforms are added up, x1, x2, x3 and x4, to form a complicated waveform which is x of t. So we can write mathematically this expression, you can see in this slide, and here we are assuming 4 waveform. If there are n number of waveforms, then we can actually adding up all these cosine waveforms to get the complicated waveform. Again all these are represented in terms of their fundamental frequency, omega 2 omega 3 omega, integer multiple of its fundamental frequency. But it is not necessary that all the components are present. Again, a case may be assumed that we have only the odd components, 1 omega t, 3 omega t, 5 omega t and so on, or we may have only even components. Again it depends upon the pattern of complicated waveform, but generally we can represent this type of waveform as this expression, where we have n number of cosine waveforms added up together to form a complicated waveform. Now coming to the case 3, we have a very complicated waveform, and that waveform can be formulated when case 1 and case 2 will be combined. That is complicated waveform made up of many simple sine waves which begin at 0, and they are added up with complicated waves made up of cosine waves which begin at some other value. So all these waveforms are actually combined together to form a complicated waveform which actually not starting from either 0 value or its maximum value. So in this case we are actually adding up the expression we have used in the case 1 and case 2. You can see that actually we are adding x1, x2, x3 and x4, which belongs to the sine waves, and x5, x5, x6, x7 and x8 belongs to the cosine waveforms, and the same 2, 4, 6 and 8 hertz are utilized. So we are actually combining case 1 and case 2 to form a waveform which is very complicated in nature. And in general we can say that this type of waveform can be represented by mathematical expression written in the slide. It must contain the sine waves and cosine waves and n number of sine waves and n number of cosine waves. So this is the third wave, which constitute a very complicated waveform, not the simpler. Moving on to the case 4, which is the most complicated case, that is case 3 is combined with the DC offset. So you can imagine we have a complicated waveform in which we have sine waves as well as cosine waves as well as DC offset. It means the wave is not symmetrical around x-axis. It is shifted either upward or downward. So if this is the case, then another term is added to this complicated waveform expression, which is A naught, and A naught is actually the magnitude by which the waveform is shifted along the x-axis. It is actually shifted along the y-axis, but it is not symmetrical around the x-axis. So basically we will get the generic expression in which we have the sine terms also we have n number of cosine waveforms as well as a DC offset. So you may imagine now that we have a very complicated waveform, and that complicated case is one in which the pattern has some irregular shape, which is neither sine wave nor the cos wave, and neither it is symmetrical around the x-axis. So all these cases can be represented by a generic mathematical expression written on the slide, which contains A naught as well, which is the DC offset, the terms for sine waves and the terms for cosine waves. And actually this is the expression for Fourier series. So by using the example, we are actually come to the point, or we actually derived the expression of Fourier series. Fourier actually claimed this, that any complicated waveform can be represented by n number of sinusoids having different frequencies or amplitude. So this is the expression basically for Fourier series. It is written in the expanded form. In the compact form you can see it in the later slide. So students, actually we have derived the trigonometric expression for Fourier series, and this equation is pertaining to the synthesis equation of Fourier series. As you seen from the example that we are actually combining multiple waveform to formulate a complicated waveform. So this is basically the synthesizing of components to formulate a complicated or final output. So this is basically the synthesis equation of Fourier series, and you can see from the generic expression that f of x, any function or any signal or any pattern, can be represented by A naught, which is the DC offset, plus summation, and from 1 to infinity. It means we have only one term also, or only one waveform also, or we can have multiple waveforms or infinite waveforms. So here it is the limitation of Fourier series, that infinite terms cannot be added using computer or using processor, or as we have a limited memory in our systems. So we have to choose the limited number of actually the components. So this is the practical limitation of continuous time Fourier series. We can solve it on paper pencil. We can uh, try to reduce our calculation to specific n number of terms, not the infinite also on the paper pencil, but we came to know the contents which are present in that signal. But practically if we want to process any real world signal, then it is the limitation, because in the real world or practical signal, we are not sure that where it is going to complete its one cycle. And for Fourier series, we can actually apply this technique to only periodic signal. So for real-time signal, we never know that when this signal complete its one cycle. It may have completed the one cycle, or it may not completed the one cycle, because the samples are coming in the real time. So this way we have some limitation to use the CTFS for practical or real world signal. So you can look at the expression, and this expression can be utilized to solve the signal analysis, and we come up with very good results on paper pencil also, by using this Fourier expression. And you can see that the expression used in the book or written in the book utilize the notation of k instead of n. We have considered the n number of terms. Here in book it is used n number of term is replaced by k number of terms. So just the notation is different, all other things are similar. And as we also have discussed the Euler's identity, and in the Euler's identity I have concluded that the any sinusoidal signal can be represented in the exponential form, or exponential form can be break up into sine and cosine. So this trigonometric form can be represented in exponential form of also, because sine and cosine can be represented in terms of exponential signal also by using the Euler's identity. So the second equation is also of synthesis equation. We are formulating x of t, which is the complicated signal, and this signal is basically we are formulating this signal with the help of adding multiple exponential signals. So here it is an advantage of using exponential form, that we have to only compute only one variable, which is c of k. In the trigonometric form, we have to calculate a naught, an, and bn. It means we have to calculate three variables, but in the exponential form we only have to calculate c of k. So this is the complex exponential form of Fourier series, both the equations are valid, only the representation is changed. So we can use either equation to solve or to analyze a signal, whichever is convenient to you. So I hope that after building up the concept of quadrature signal, sinusoidal signal in real time, relating it with Euler's identity, and after discussing the continuous time Fourier series in much detail, and by considering relevant example, and it is also very easy, which I have discussed. So, and by that example we actually derived the expression you have seen this and then written on the last slide, this slide, that we actually, by with the help of example, we actually derive this expression. So I hope that the concept of continuous time Fourier series is clear to you. And again, if you have any question related to CTFS, you may write or comment it on the classroom, or you may personally send me an email, or you may note it down and you may ask me in the live session. But I hope that you are getting my point, all the points I have discussed in these two lectures, to build up the basically your understanding towards the continuous time Fourier series, because if you understand this, then other techniques are similarly derived like this. We will not go into the derivation of all these techniques because we have done with one, and you have now gained the concept how it is derived. We only worked with the we will only now will see the final expressions, which are the analysis and synthesis equation. In this slide we have only derived the analysis equation, synthesis equation. So we have to discuss the analysis equation in the later slide. So if you have any question or query related to these lectures, you may note and ask me in the live session. So winding up the session, thank you.